Ok. Allora, benvenuti, grazie di essere qui. So I switch to English, but today I'm proud to have as a speaker Professor Thibault Damour, who has been, but he's still a professor at IHES, Institut for Hautes Études in France, and he studied a lot of different topics in physics, so it's difficult to collect all the contribution of Professor Damour in his career, but essentially in the last few years focused on the dynamics of black holes, gravitational waves, and so on. So I'm very happy because we had a talk by Professor Damour some years ago, just after the discovery of gravitational waves here in Institut. Thank you again for an update about this very important class. And okay, I have to thank Donato B to organizing this talk, because it's thanks to Donato B that we have this connection with Thibault Damour, this kind of important research. And then I switch again to Italian, so that salutiamo tutti gli studenti e i professori, sia quelli in presenza, sia quelli connessi via web, che ci stanno guardando, del Liceo Pascal di Pomezia e del Liceo Grassi di Latina, con cui come istituto abbiamo fatto dei progetti di PCTO proprio su questi argomenti. Quindi che sembra un po' strano che lavoriamo con i ragazzi di liceo, però speriamo che alla fine di questo percorso, insomma, qualcosa sia passato. Allora, io lascio la parola a Thibault. Sì, ecco così.
Full screen. We leave this on the left. Okay.
Tu parles, tu cliques.
Ah, but I move them with this, no?
Yes. Aussi.
Ah, either. Okay. Okay, so thank you. It's a pleasure to talk here. I hope I will come back here on other occasions in the future. Don't hesitate to ask questions if something is unclear, because if most of you get lost after the second slide, then there is no point. So I will talk about black hole binary dynamics. So let me summarize what is the problem. The problem is to solve Einstein's equations, where this is, well, one is trying to solve approximately the geometry of space-time. In this picture, there is a representation of a space-time where time goes up and space is horizontal. And this is not a DNA molecule, but these are two black holes with their horizons going around for hundreds of millions of years, getting closer and closer, faster and faster, emitting gravitational waves until they are extremely close, and then they merge, and at the end they create a black hole. And the explicit form of Einstein equations, so Einstein equations are a system of partial differential equations of second order, which are hyperbolic in the good gauge. And this is the explicit form, actually, of Einstein's equations, where the comma mu means the second derivative of the metric G, and this is the inverse of the metric. So you see the nonlinear terms. In the case of black holes, there is no right-hand side of Einstein's equation because these are made of vacuum. So actually, you solve the Ricci equals 0 equation. And what you want to extract, because this is what is used for the observation, is what is the gravitational wave emitted at infinity due to this motion. And essentially, the signal is for hundreds of millions of years. You have like the sine wave, where not much happened. The sine wave has a slowly increasing amplitude and a slowly increasing frequency. But during the last orbit, this accelerates, and then you see that the amplitude increases more importantly, the frequency, and then you have the merger of the two black holes, and then the final thing. So this problem has been solved by many years of work by many physicists using several different approximation methods, because it is impossible to have an exact solution for this problem. So you need to combine various approximation methods. The time-honored method in this business is the so-called post-Newtonian approximation, which is an expansion. It's a combined expansion in small velocities. So you assume formally the velocity of light is very large in units where the velocities of your objects are, let's say, 1. So that you have a small parameter, v square over c square. And you have also the fact that the gravitational potential in general relativity between two objects has a small factor 1 over c squared. This is another small parameter which is dimensionless. So you have a double expansion in these two small parameters. But in the past and recently, I will discuss that this has become more prominent, you can do another approximation where you don't make the approximation that the velocities are small. The velocities can be of order of the velocity of light, but you consider two bodies that are far away from each other, so that you still have a small parameter, which is gm over the distance, or the impact parameter b in the case of scattering between the two, with c squared. Then I will describe other things like multipolar post-Minkowskian. Let me say match asymptotic expansions is a crucial thing in the sense that black holes are very complicated objects. They are both very simple and conceptually subtle. It took 50 years to understand what they are. And a priori, as they are extremely strong field objects, you could say you cannot deal with any approximation method because they are strong field things, okay? But actually you can if you use the method of match asymptotic expansion, which you use several different approximation methods. One of them is near the body, one is far from the body, then you combine all this. Then you have the self-force that I will not describe, which is when there is a large, when one mass is, well, it's a binary system with two masses, M1 and M2. When one mass is much smaller than the other one, you have another small parameter. I will mention the effective one-body method. Numerical relativity started giving results only relatively recently in 2005. And then the main part of my talk will be to say that now there is a development of new methods for attacking this problem using quantum field theory techniques and scattering amplitudes. And these methods are very promising. They have not yet given results which are replacing any of the previous results or even complementing them in an important way for LIGO. But in the future, probably it will be more and more important. And then there is another development that we developed with Donato Bini and Andrea Geralico, which is the tutti frutti method, which actually is what gives the best results today. Now, the post-Newtonian, so just as a reminder, why, what means the post-Minkowskian expansion? First, I should say that in the 80s, actually, we had started using the post-Minkowskian. So post-Minkowskian means you do not make the small velocity approximation assumption. You just say, I have two bodies and I make a weak field expansion. I just assume formally that you can expand in the Newton's constant G as a formal parameter. So G appears on the right-hand side of Einstein equation. When G equals 0, you have flat space. And then in first order in G, you have linearized gravity. Second order, things start becoming nonlinear. And then at the time, we could go to second order in G. And already there, we had non-trivial integrals to compute, okay? And we realized at this time that it was difficult probably to go beyond, because even this integral was non-trivial to compute. And the new methods that are developed now is that using quantum field theory techniques, you can compute these integrals that look difficult to compute at the time. Anyway, as they were difficult to compute at the time, another method was pursued, which is to say that when you have, so this diagram means that in space-time you have two world lines, which means the trajectories of two bodies in space-time. And this thing means that they interact by linearized gravity. So one particle creates a gravitational field which acts on the other one. This thing means that a particle creates a gravitational field, but in a nonlinear way. You take something quadratic in the gravitational field created by this particle, which then creates a secondary gravitational field acting on the other body, okay? So this is this diagram, and then you go to higher and higher things where you start having non-linearities in between the two bodies that you have to solve as PDEs, order by order, okay? And in the post-Newtonian approximation, these diagrams here, I mean, these lines, wavy lines, means a particle, I mean, means the gravitational field is emitted as a retarded wave in space-time, solution of the D'Alembert equation. But if you expand a solution of the D'Alembert equation formally, which is inverse Laplace, you get a set of Poisson equations, okay? That you have a Poisson equation, an iterated Poisson, and it's much simpler to iterate Poisson operator, the inverse Laplacian, elliptic operator, inverse, than hyperbolic operator. So this way, one can go to high orders, and then at some order, there is a sort of effect which happens, which at a very high order, what happens is the system can emit a gravitational wave which would go to infinity, but it is backscattered on the nonlinearity of space-time and strikes back on the system, which means that the Newtonian force, I mean the gravitational force here acting on the two bodies, is a function which depends on what happened in the infinite past. You have something which is non-local in time. Just to say, these are called tail effects. Now, this was to compute the motion of two bodies, okay? And by the way, if ever one of you, like Massimo, wants to do the same thing for other objects, like the standard black holes of general relativity, one has to redo everything and take into account a very high order calculation in something having different objects than the standard black holes. Now, there is another very important aspect. Here I was talking about the motion of these two world lines, so it's still a space-time diagram. Time goes up, space goes on. Here, I have decomposed the space-time around these two objects in a zone near the two objects, the near zone, in which you can use the post-Newtonian expansion I was mentioning, because in this zone, the effect of, I mean, the fact that the propagation is at the velocity of light is a small effect, because when you're in the near zone of a radiating system, the distance small compared to the wavelength, things are quasi-instantaneous. But if you have then in the exterior zone, which is from this radius to infinity, easy, you have to take into account the propagation of gravitational waves at the velocity of light and nonlinearities. So this method, which was developed by Luc Blanchet, Valayer, and myself, is to decompose the space-time in various regions, solve Einstein equations in various regions, and then match the result to be able to compute the waves emitted at infinity as a functional, finally, of the two world lines, okay, which is what you want. Because you could not compute them directly, okay? You need to do this by successive steps, and then it was shown to be efficient. Let me give a recent example of how efficient this thing was. First, I will mention this later, but you can decompose, roughly speaking, the problem of the motion of two bodies in saying you want to compute what is the Hamiltonian, the potential of interaction of the two bodies, to know how they go around each other, but you want to know also how much energy and angular momentum they lose to infinity, because you are going to say that you need to add radiation reaction forces on the dynamics, which take into account the fact that they lose energy, okay? The dynamics of the system has been computed fully at the fourth post-Newtonian level, which means V8 over C8 smaller than Einstein, so it's a very high level of approximation, which took 20 years to be obtained. And in the recent years with Donato and Andrea, we could push this even to the next level and the next to next level, but there are two numbers here at the next level that we cannot compute. They're pure numbers that are simply unknown, but all the rest is known, okay? And now, from the point of view of the emission of gravitational waves, this formula here is the flux, energy flux into gravitational waves at infinity, and in for two bodies going along circular orbit. which, by the way, is a very good approximation because we know that in nature, all the binary systems, we are going to talk about two black holes going around each other. In general, in nature, when two bodies go around each other, like the Earth around the Sun, the trajectory is not a circle, it is an ellipse. But you prove that because of radiation reaction, quickly all those elliptic motion becomes circular, quasi-circular, although they shrink a little bit. And therefore, it's a very good approximation to solve only what is the emission by circular things, which simplifies the computation very much. The first term in this formula, which is 32 over 5, and a term which is expressing this parameter x, which is essentially v squared over c squared. The first term was obtained by Einstein in 1916, and more correctly in 1918, so it's called the quadruple formula. So Einstein computed gravitational waves and said, okay, the first term is this one here times this coefficient. And you see the next term was computed actually in the 70s, and all these new terms were computed only more recently. And in particular, the last two terms here have been computed only very recently. The paper was published last week by Luc Blanchet, who have done studies with me on this problem, and we have been driving force to push the accuracy of this computation. Okay, so this is the level of accuracy that one has today, which is important for applications. Now, the results I have shown before. Yes, question.
How did you get the non-analytic terms?
Yes, you're right. These non-analytic terms, they come actually from what I was saying before, the tails. The tails is this non-locality. So actually what happens, the reason why they are logs, and also why they are Euler's gamma somewhere, here, gamma I, as Pierre Devine taught me and other people taught me, is actually we are computing integrals with sources which go on helical motion, which means these are exponential integrals. You have integrals, and then you have also exponential in the integrand, and then this gives logs and gamma Euler, and so you have non-local effects in time. Okay. If everything was local, you would have something analytic in it. Now, all the results I've shown before, like for instance, you could say this one is saying this gives. So Einstein said to lowest order, the flux emitted is due to the time varying quadrupole of the system. Then you said there is a first correction in v squared over c squared. Then a second correction in v cube over c cube. Then up to, v9 over c9 here, okay? Then these corrections are necessary and very important when v over c is small. When v over c is small, you improve the accuracy, okay? But actually, if you want to compute what happens in the last orbit, v over c is 1/2. And then you find that the coefficient in front of this is so large, which means the radius of convergence is of the order of 1/2 or less, which means it is illusory to add more terms because near the last orbit, this expansion is 1 + 1 - 1 + 1 - 1, does not converge at all, okay? Which means it becomes, in a sense, useless to describe what happens in the last orbit. And for many years, people, especially in America, said it's impossible to use analytical methods, only numerical relativity will describe what happens, okay? But some of us in Europe were saying, no, we can invent better methods. And in particular, with Alessandra Buonanno, when she was a postdoc at my institute in 2000, we proposed a method called the effective one-body method, which essentially is doing the following thing. I will not describe it in detail, but just to say, instead of describing, first you need the results of the computation before. You need perturbative results on the two-body problem. But then you try to say, you want to resum your results to replace a perturbative expansion by something which is better behaved when they are very close. And the idea is to replace the two-body problem by the problem of one particle of mass mu, the effective mass, like in Newton theory, you know, if you put a particle, if you have the two-body problem, it's equivalent to a particle of mass m1, m2 over m1 plus m2 in the potential of the two bodies. So the idea was, can we do something like this in general relativity? And then we constructed an effective metric in which a particle of mass mu, which goes around this, reproduces the perturbative results, but the fact that you re-express it as an effective one-body problem helped in resumming the thing. You could describe the last orbit. And then we said, our method describes the two black holes up to the moment where the two black holes touch. So we use the description that we obtained this way up to the last orbit, which is here. And at the moment where they touch, you say, you make also a coarse approximation. You say, I have two black holes. You can think of two black holes as two soap bubbles. You know? And when you have two soap bubbles that touch each other, what happens is they become one bubble, okay? And the same thing, I mean, at the time, we just said, let's assume the same thing happens for horizon, that when they touch, they become one black hole. But evidently, when the black hole is formed from this black hole will not be immediately in the equilibrium state. It will be in a bad state, deformed. And then you say, but the black hole which is deformed, we know from many years that it will vibrate because it was discovered long ago, in particular by Tullio Regge and John Wheeler, that black holes are dynamical objects that can vibrate. There are vibration modes that were computed. And then the idea was, we said the signal after the moment of merger is a superposition of the quasi-normal modes, of the vibration modes of the black hole. And we could determine the superposition from saying it is a continuous function with two derivatives, C2, okay? And then in 2000, we published a paper where we said we predict that the gravitational wave signal will be like this, okay? And nobody believed us, especially in America, where they continued saying for 5 years that only numerical relativity will get the result, and this is nothing, and it will be very complicated, okay? But a few years later, thanks to particularly a young postdoc in Caltech, Pretorius, France could compute the first signal. And in this paper of 2007 with Buonanno Pretorius, they compared the first numerical relativity computation of the signal and the effective one body purely analytical, no information from numerical relativity. And as you can see, this is the evolution of the frequency during the merger. They are quite close before merger. And even after merger, it's not exactly on top of it, but it's getting close. A few years later, in collaboration with Luciano Rezzola and others, we could do better comparisons. And here you see that the EOB and NR are very close to each other, but there was still a difference. But the difference is only 10%. Like so I don't know if we were lucky and we should not have got the good results, but the fact that the very naive or not so naive, but the simple effective one-body method predicts 90% of the signal. But once you have numerical relativity, you can say, I can improve the effective one-body by using some information. Numerical relativity is much better when you are described in the merger and after the merger. So we use this information to improve the analytic description and the type of waveforms which are now developed, particularly by Alessandro Nagara and his group in Torino and by Alessandra Bonanno in Berlin, now gives agreement. Here on this plot, you have two waveforms, a numerical relativity and an EOB waveform. But it is impossible to see the difference. Actually, there is a very small difference here, okay? So this is the type of it. Anyway.
So for you, the waveform is this strain?
Yes, the waveform is H. Yes, so just to be clear, in general relativity, the metric of space-time G mu nu is the sum of the Minkowski metric, which in the Euclidean space would be delta ij, the Euclidean metric, Euclidean Pythagorean theorem, and the modification of this metric called Hij is what we call the gravitational waveform, and this is what is measured directly, okay? And this is H, which is this gravitational waveform. And the waveform, which has been observed in 2015 for the first time, has an amplitude compared to 1, because 1 would be the Euclidean metric, 10 minus 21, 10 minus 22. It is an extremely small fluctuation here. It was bigger at the source, but it decays like 1 over r.
May I ask, what do you mean by measure? How do you fix the measure time?
The what? In the method. Yes, in the method, the merger time is fixed by the EOB internally, okay? There was a criterion which was essentially traversing the light ring, okay? Because it was understood by Fini and his group, there are many Italians in this business, that when there is something like, in the case of a test particle going on a black hole, that there is a structure around black holes, which means that gravitational waves can go around in a circle. And when you reach such a radius, this is the transition between a wave that goes to infinity, like flat space, and a wave which is linked to black hole structure, okay? And this was the definition of merger, and we were attaching the QNX after crossing this, predicted in the method. Now, so let me describe one technical point of the, there were questions here on the Zoom? No. Of the effective one-body approach, which is, so I said in the picture, the perturbative description of two black holes would be, you know, two world lines interacting at high orders, like this is 3 loops, you know, because you can count the loops here. And you compute this in a perturbative manner. Then you want to say, let me describe this in an equivalent way as being the motion of an effective particle of mass mu in some effective metric, but you don't know the effective metric. So you have to construct the effective metric from the perturbative results. But what you find is that this effective particle, it satisfies what would be called, let's say, either an Hamilton-Jacobi equation, a mass shell constraint, which is of the type mu square, the square of the mass, plus a term quadratic in P. This is the usual Hamilton-Jacobi equation for a particle in first spacetime. But you need to add also terms of higher order in momenta, as we found at the cubic order, you need this. And then you want to say, how can I compute the equivalent of this is in this language? But at the end, there is a procedure which says, I take the perturbative results and I replace them by this much simpler equation, the particle u moving in some geometry, effective geometry G mu, with some extra terms which are nonlinear in more than quadratic in momenta. And okay, I will not describe the quantum aspects of this and what I know, but what I want now to say, this story up to now was what was developed up to 2015, 2016, which has been used by LIGO and Virgo to detect gravitational waves, okay? But at that time, I had thought that maybe there would be conceptually a way to understand better the effective one-body approach and gravity by treating another problem, which is not two black holes going around each other essentially in circles, but two black holes scattering, which means you send two black holes with opposite velocities, and they pass at a large distance from each other so that they come out along deflected trajectories. And this is called scattering. And then in the case of gravitational scattering, the information you have is what is the scattering angle. Okay, you start from one direction and you come out with a different angle. And this scattering angle is a function of the energy, incoming energy and incoming angular momentum or impact parameter. So you have a function of two variables. And the idea, which is gauge invariant, as you said, this function is totally independent of coordinates in space-time. So it's a nice object. And the question is, if you can compute this function, can you transform it in an EOB Hamiltonian? And I have shown in this paper that indeed, you can, in a very simple way that I will describe, transform the scattering information into an effective one-body Hamiltonian, which then can be used to describe circular orbits. Once you have the Hamiltonian, you can describe the orbits you want. And then at the time, I had, I was here urging, yes, here I was urging amplitude experts because I knew after discussions with some people, in particular Pierre, that I knew that people were working on the quantum amplitude point of view in computing scattering amplitude. So I was urging amplitude experts to use their novel techniques to compute the two-loop scattering amplitude and to get new results on this, okay? And a similar idea was proposed later by these people. Now, what is this dictionary? The dictionary is actually extremely simple in the sense that, at least for the conservative part, and the idea is, if you know the scattering angle, I said the scattering angle is a function of the total energy of the system and total angular momentum. But actually, when the two bodies are far away, people could enter, but they look from the window. No, they just pass. Not interested. When you take a large angular momentum, it means they are very far apart. So it means the interaction is small. And therefore, there should be an expansion in inverse of the angular momentum, okay? So what you do is you compute the scattering angle as an expansion in inverse of the impact parameter or inverse of the angular momentum, and each coefficient is function now of the total energy, okay? And at the time where I wrote my paper, the first order in this expansion and the second order was known, but what I had written is if you know things to any order, by very simple formula, this is scattering angle, you compute Q2, this is scattering angle at order cube, you compute Q3, then the effective one-body description is just described by some metric G mu, and then 1/r square corrections, and 1/r cube corrections, where the coefficient of 1/r square are just functions of k. So a very simple dictionary. And at the time, I looked at what existed in the literature. And the only result that existed was a result coming from string theory of Daniele Amati, Marcello Ciafaloni, and Gabriele Veneziano, in which they had computed in the ultra high energy limit what was the scattering angle of two, let's say, gravitons, or low energy modes of a string passing. So they have, gravitons are massless, but if you give them a high energy, by Einstein E equal mc squared, this is like mass, energy is mass, so they scatter like massive particles. And then they could compute by using the econal approximation and Regge-Gribov theory, they could compute things to second order in G, okay? And this was the only result that existed at, let's say, at an interesting level. So, and I could use in my first paper the result of Amati, Ciafaloni, Veneziano and say, okay, I can, in the ultra energy limit, convert the result in some information about the Hamiltonian of two black holes, okay, in the ultra energy limit, and I could compute this. And then, in the meantime, yes, so I want to say that now there are certain issues because the most efficient techniques now in physics to compute scattering is not classical scattering. You can compute by perturbation theory classically, when two particles attract each other, how they deflect. There is like a Coulomb force, a Newtonian force, relativistic, but it's quite complicated. I mean, the formalism, although in principle you can write equations to any order, it's difficult to solve it. Why, if you are in quantum field theory and using many results in quantum field theory, there are efficient way to compute the quantum scattering. But the problem is that the perturbative expansions that you learn in quantum mechanics is valid when this parameter, which is the analog of the fine structure constant, G, let's say the square of the energy, the product of energy of the two particles divided by h bar the velocity, must be much smaller than 1, because you have an expansion in powers of it. But in the classical problem of two black holes, this quantity is enormous, much bigger than 1. So how can you use an expansion for small alpha in a regime where alpha is very large, okay? That's the conceptual question. And now there are several good answers. I mean, at the beginning, some of the people did not understand this point. Only Gabriele and colleagues understood that very well because they said, we are in the econal regime. The scattering amplitude is not a perturbative expansion. It has to be exponentiated, and then it is the logarithm of the amplitude of the etc. I will not enter into details, just to say that these are subtle issues. Then you can use these results. Yeah, what I said is, in this approach, the interaction between two bodies in a relativistic way for arbitrary velocities, as close as you want to the velocity of light, is equivalent to a Newtonian problem with a potential 1/r plus 1/r squared plus 1/r cubed, except that the potential depends on the energy in a non-trivial way, okay? And then, if you quantize this system, you can write a Schrödinger equation and you can compute the scattering amplitude, and this is identical to the classical part of the quantum amplitude. Let me not enter here. Then the first breakthrough came from the group of Zwibern, who was the first one to be able to reach the level which was beyond what was known, the same level G cube as the level that Amati, Ciafaloni, Veneziano had obtained, but the new result was, this result was valid for all, not only in the ultra-relativistic regime, but for any even small velocity. And so they got these beautiful results. So here you see you start seeing some transcendental function, arc-sinh of square roots of gamma minus 1. So this was a two-loop level computation. And then when one uses their results and compare it to the previous result of Amati, Ciafaloni, Veneziano, there was the surprise that they did not agree, that actually the results of Zwibern did not have a high energy limit because there was a logarithm violation of the high energy. And then for 1 year, it was a puzzle in the sense, Zwibern said, no, it's no problem, but Gabriele and myself said, no, it is a physical problem. We have to understand why this beautiful result does not agree with another beautiful result and what we know from classical physics, okay? And in the meantime, with Donato and Andrea, we had given actually confirmations that the formula of Zwibern was correct. Although at some point I dared to say maybe there is an error in the thing, Zwibern was not happy when I said that. So for 1 year, it was a problem. In the meantime, Alessandra tried to say, maybe we can use this result for LIGO, but actually these results are not very convincing for saying, as such, this result as it exists is immediately useful. And the problem came, the solution came from a better understanding of what we are talking about. Actually, in the physical problem of the interaction of two bodies, you can think that let's say the force, the derivative of the momentum of each particle in a two-body system is a sum of terms. Some of these terms are invariant under time reversal, and they contain an even number of velocities v over c, so that if you change v minus v by changing the sense of time, nothing changes. But other terms contain an odd powers of v over c, and so they are linked to time odd effects, non-time reversal. And what is non-time reversal in the dynamics of two bodies? This is linked to radiation reaction and the loss of energy in the future and not in the past. If you solve with retarded potentials, you should have time dissymmetry between the past and the future. So it means at some stage, one has to take into account radiation reaction. And actually, this is at this point that people realize that the calculation of Zwibern had completely neglected or ignored these effects. And then it became clear that we needed to take into account this, that here is a sketch that in space-time, this is the sketching of two bodies. And in classical physics, you can define from it a time-symmetric version of this, which is called the Fokker-Wheeler-Feynman approach, in which you say that the interaction between two bodies is still time-symmetric, that when you solve D'Alembert equation, you use as fundamental Green's function the time-symmetric Green's function, and not the retarded Green's function, or the Feynman one, the quantum complex, which is time-symmetric. And why classically you should lose energy at infinity, okay, and things like that. So this was so it was understood. In particular, the first paper which said, radiation reaction effects will play a crucial role, and you must take into account, was a paper of Di Vecchia, Heisenberg, also Veneziano in 20, and then discussing, and in their paper. What they had shown, I will not enter into details, is that if you take immediately the high energy limits, you see that indeed radiation reaction effects in the high energy limits are important, and they could recheck the old result of Amati, Ciafaloni, Veneziano, because at some point people said, maybe Amati, Ciafaloni, Veneziano was wrong, and things like that. So this reinforced the puzzle, Amati, Ciafaloni, Veneziano was correct, and it left open what is exactly the effect, which means that you can take into account radiation reaction in the scattering. And this came, so I was lucky to be able to do a very simple calculation, which is computed in one line, really. And using a previous result we had with Donato Vini in 2012, which is that when a binary system loses energy in angular momentum, from the computation of the energy loss and angular momentum loss, you can immediately write a simple formula which says that the scattering angle is modified by a quantity which is proportional to the energy loss and angular momentum loss. And using this formula, it was enough for me to compute the angular momentum loss, which happens to be at a lower order than the energy loss, so you don't need the energy loss for this. And then I got this formula, which contained this transcendental, transcendental is a big word for just arctangent, okay? It's arc hyperbolic tangent of the velocity. And then this formula reconciled exactly. When you add this term, it made to the Bern result, it gave exactly the result of Amati, Ciaffolini, Veneziano. And since then, this has been rederived by many people in different ways. Now, in the meantime, people started understanding, okay, we need really to clarify what are the various ways, starting from a quantum amplitude, to get a classical result. And today, there is not a unique answer. There is a menu of possibilities, because each year people say, maybe I can use this, and this is more efficient, and I am more efficient than you, and okay. And one of the beautiful formalisms is by crossover, maybe O'Connell, which says, okay, let's compute observable in quantum field theories. What is the momentum of the outgoing particles computed a la Dyson in the initial state with the S matrix, okay? Although it means you need more computations because you need to redo integrals. That's why there are more efficient methods like the high mass expansion. And then, but for this also, one of the first really new results that came of the quantum field theory method was this result of Hermann, Para-Martinez, Ruf, and Zeng, where they could compute the total loss of energy at infinity for arbitrary velocities. Because this total loss of energy, as a function of the impact parameter and of the relative velocities, people had computed the waveform, okay, but they could not compute the integral of the waveform giving the energy loss. While here, by using subtle methods, like, okay, I will not enter in the details, they could compute this, which again contains this arc-sinh function, okay, and a log, okay, so we are still at the level of the log. And this raises a puzzle that I will discuss on the next transparency. But now, Bern has obtained, the result at the third order in Newton's constant. And then Bern had said, but our method can go to higher order, okay? And then he was, with his group, in particular Julio Para-Martinez, he could compute scattering amplitudes and conservative binary dynamics at the next order, except that I said at some point that we knew classically since the 1980s that when you have two bodies interacting in space-time, they interact via this non-local thing due to the waves scattered at infinity going back on the system. And when you do a quantum field theory calculation, this comes from soft gravitons somewhere that you can separate from the calculation. And therefore, you can do a calculation which does not include that, which is easier to do. And this is what they did first. These are the so-called potential gravitons. And now you see results where you see that the amplitude and then the scattering contains complete elliptic functions. So in QFT language, it means, you have the level of transcendentality like the logs. When you reach the complete elliptic functions, you reach another level of complexity that is reached by gravity. And these things contain infrared divergences. But these infrared divergences is precisely, and we have with Donato proven before, that the coefficient of the infrared divergences is precisely the energy loss linked to tail effects. And they could actually recompute the energy loss using our results. So this is divergent because they did not include the other part of the calculation, okay? Then they did include the other part, okay, which is linked to these tail effects or this kind of soft gravitons. When you add the other part, the divergence cancels, so it's good. You have a finite result. And then we could, and they were also very happy because in the meantime, having the method we had developed with Donato and Andrea, we had pushed post-Newtonian methods to compute quantities to very high order. And actually, we had computed terms that were unknown before, and they could check the exact formula against our expanded results. And they were very happy because in this business, as calculations are very complicated, you trust the result only if you can compare to another independent calculation and see that there is an agreement. Because you see, when you get a number which is like this, which agrees, it's a rational number, but when two numbers like that agree, you start feeling it's correct, okay? Anyway, let me just say a few words about the method we developed with Donato Bini and Andrea Geralico. This is called Tutti Frutti. Why it's called Tutti Frutti? First, because when I was a kid, we had a game card in which you could use separate rules. And then at the end of the game card, you could say, I put all the rules together, and this was called Tutti Frutti, which I thought was used in Italy. Apparently, it's never used, Tutti Frutti, but then it's put together, you know, all fruits. And then I will not describe the thing. It's a method which combines 3 and 4 of the various approximation methods that I did not describe in detail, like self-force, post-Newtonian, post-Minkowskian scattering, polynomiality, some things. Okay. You use everything you can think of, you combine them, and it's very efficient. At the end, you determine everything modulo just 2 pure numbers, and this is sketched here. So we could reach, you know, reach things at a very high order, modulo just unknown parameters, and we could check things and also obtain new results. I will not describe the results, but maybe in the future, this will be part of the game for LIGO in the future. Now, in the meantime, separately from Zwibern, who said, I use really quantum scattering amplitudes, it was realized in particular by the group of Rafael Porto that one can use actually the old-style classical perturbation theory, because old-style classical perturbation theory is that you describe the 2 world lines, and these 2 world lines, they interact by a gravitational field that you solve by solving Einstein equations at each order. You know, at lowest order, the gravitational field is a linear function of the other world lines. At nonlinear orders, you need to compute these complicated integrals, and with retarded propagators, put back there, compute the scattering angle order by order. And he showed by using this old-style perturbation theory, but using QFT techniques to compute the integrals, combining, you know, the 2 aspects, classical and technology of quantum theory, he could push the classical accuracy at very high order. And in particular, this year, in March 2023, he was able to get the full answer at the order G4, the same order as Zwibern, but including radiation reaction. And these results looks like this. This quantity is the change of momentum of one body, so it is essentially the scattering angle of one body deflected by the other body. And each coefficient h is a complicated polynomial in the energy of the system. And independently of him, with Andrea and Donato, we could actually also derive by much simpler ways, actually, exact results linked to this, and there was full agreement between his result and our result. And I remember we exchanged with Rafael Porto, and he was very happy when you told him, okay, we have this result. He said, okay, it's agreed with mine. Then he published his result immediately because he knew his result was correct only after having checked that. Just to be sure, because if you forget one term, you know, you are wrong, and you don't want to publish it. So he was happy about this, and we were very happy also. I should just mention in passing that all these beautiful results, they open interesting conceptual puzzles, problems, you know, which are not understood today. In particular, I said one could compute the energy loss during for all velocities when two bodies scatter. But if you take this energy loss and you say, I compute it when the two bodies go very fast, you find that the energy lost to gravitational waves is bigger than the energy of the system you have. So clearly there is something wrong. You must take into account some effects to have consistency with the physics. Also, the same is true for the angular momentum loss when you go to higher order, to the G cube order, which has been computed by Manawa and Shen. You have, so there are several subtleties also, because when I first did the calculation of the angular momentum loss, it was surprising to people, especially Gabriele Veneziano, because as the energy loss of two systems starts at third order in G, and quantum mechanically, you get an energy loss because you lose gravitons. Now, each graviton has an energy, h bar of omega, and has spin, angular momentum, 2h bar, okay? So you should lose angular momentum only if you lose gravitons. At order G square, where you have no loss of energy, you should not lose angular momentum. But I have known for 40 years, actually, we have computed this in 1980, that there is angular momentum at lower order. So it's a puzzle which has a kind of resolution linked to Van-Gog's theorem or something. There are many things, but it shows that conceptual problems arise. And I should say that there exists a true discrepancy now between two different calculations at the fifth post-Newtonian order between results of Four-Pastorani Bloom line on one side, who use the effective field theory approach to the post-Newtonian computation of the dynamics of two bodies, and our results, which uses this tutti frutti, and there is really a number which does not agree. And although we have been working hard with Donato and Andrea on solving this, we don't have a full resolution, and nobody has a full resolution yet of this problem. Let me also mention, because I was lucky to collaborate with many Italians, recent work with Piero Retegno from the Torino group of Alessandro Nagar, and where we compared the existing post-Minkowskian expanded formulas for the scattering of two black holes to numerical relativity. Because actually, years ago, in collaboration with Luciano Rezzolla and others, we had computed numerically what is the scattering angle of two black holes, numerically, and then we have data of this scattering angle. Now we have analytical formulas that say in the large distance limit, these two should agree. But what is interesting is that this numerical relativity, they are not in the large distance limit, because the two black holes actually, they come so close that the scattering angle is 360 degrees, you know. They come, they get very close, and then they come not at a small scattering angle, you know, they go back where they went from, essentially, or more. And what we did with Piero Retegno was to use the effective one-body description. And our results, so I will not describe the technology. Actually, the calculations are very simple, because in effective one-body, the very complicated scattering, you know, of two bodies is summarized by an Hamiltonian, which has a potential with 1 over r, 1 over r squared, 1 over r4, 1 over r cubed, 1 over r4. That's all. So it's a Newtonian problem. The coefficients of this coefficient is not Gm1 and 2, it is the energy times something. So the complicated calculation give these coefficients, but once you have these coefficients, you can compute the scattering by a formula you find, you know, in Landau-Lifshitz mechanics, page 10. Or any book you like of classical mechanics. And then we compare the numerical relativity data to various approximations. Like for instance, this is the scattering angle in radians versus the angular momentum of the system, okay? And the numerical relativity data are here. If you use the post-Minkowskian expanded results, that is to say the perturbation theory, which says the scattering angle is, you know, 1 over the angular momentum plus 1 over angular momentum square, like a perturbation theory, like a Taylor expansion, the inverse of the angular momentum. You get these curves. At one post-Minkowskian, you have the red curve. At 2, 3, 4. So, but you see that the best approximation you have today is here, while the numerical relativity here is a factor 2 above this. So this is saying the perturbation expansion is bad, is wrong by 50%. But this is normal because you scatter by 360 degrees. But if you reorganize things by saying, I will use an effective one-body description, I have a potential, and now I compute the scattering angle into an effective one-body potential, which has the same perturbative information, it's 1-to-1, but which has repackaged it in a different way, then you get this. You get an extremely nice agreement, strikingly good at 4 p.m. And now you see 1 p.m. is still bad, 2 p.m. is here, 3 p.m. is start being very good, and 4 p.m. is on top of the numerical. So it just shows that indeed resumming the thing in effective one-body, even in scattering, can be quite useful. Now, just to finish, recently there have been computations not only of the interaction of two bodies, the scattering and let's say the Hamiltonian or the potential between two bodies, but of the waveform, that is to say, the emission of gravitational waves during scattering. Okay, the waveform, what was at the beginning. You know, I have shown the waveform for coalescing, which are here. I'm talking about the waveform just for scattering, so it has less interesting feature. You know, it's a waveform like this. But this waveform, so first was computed at the first post-Minkowskian approximation, which means linear in G by Einstein in 1918. But at this order, nothing happens because at lowest order in G, the waveform is Gm over R, Gm1 over R1 plus Gm2 over R2. It's the sum of two static things by two particles that move on straight lines. So actually, you don't emit energy or anything. You have a constant waveform, okay? So this is trivial from modern point of view. The second order, G squared, was first computed in the end of 70s by Kovacs and so on, in the time domain. And recently, it has been computed by classical calculations, which were computing some integrals the same I have shown before. Now, this computation has been redone using now quantum-based techniques by several people, in particular, using ideas of Johansson, Uchirov, Goldberg, Ridgway, Luna, Nicholson, O'Connell, White, and recently by the group Vernizzi with the Massimiliano Riva and Bautista and Simonsen. All those results agree with themselves and give a much more complicated formula that we will see on the next slide. And very recently, 3 groups, one with Stefano De Angelis and Gabriele Travaglini and others, and there are Italians all over, except this one where there is Radu Golban and then Carlo Heisenberg, which in spite of its name is Italian, just for you to know. They computed independently the waveform at the so-called one loop level, the next order, which means this at one loop, by different methods. The results agree. Okay, I will not describe the things. There is the whole technology of what is the best way of computing this. And now we are working with Donato and Andrea so the waveform at the end is given proportionally to an amplitude, a scattering amplitude, emitting a graviton. So it is, you know, 2 incoming particles and 3 outgoing particles because you have the 2 original particles that come out, and then the graviton as a 5th particle, okay? And then it is given by a perturbative expansion in powers of kappa, where kappa is square root of G, with this thing, except that actually this thing is given in a Fourier domain, and if you want to compute the waveform even in the Fourier domain for the waveform, which is the Fourier transform of the waveform as a function of time, the waveform is just a function of time. You could say, okay, I do Fourier transform, I have the waveform as function of omega. But to get the waveform as function of omega, you need to do another integrals over 4 momenta, I mean 2 momenta, 4-dimensional momenta with this thing. So although they published this interesting result, you still have work to do. And at so the level of Einstein 1918 is this. It's trivial linearized gravity, okay, nothing. And at the next level, you have this explicit formula, which is simple by the standards of what you can do today. And at the recent level is given by a formula which looks simple, although there are a few logs here and there, except that this term, which is for instance a rational term, is a rational function of 8 independent Lorentz invariant scalars, which has spurious poles, which has hundreds of thousands of terms. And we are fighting with Donato, including yesterday, to show that indeed it contains useful information. Because of the spurious poles, this is difficult. Let me just conclude. The conclusions is that, as I have summarized, the analytical approaches to gravitational wave signals, by contrast with the purely numerical way, you say, okay, I pick computers, I compute numerical signals. It takes 2 months to compute the waveform of one coalescing black hole by numerical activity. You need millions of waveforms to do data analysis, so you need an analytical description of the waveform. And now we have a suite of analytical methods which have been useful, and in particular the effective one body together with others, but the post-Newtonian results. And it is important for the future, where now the LIGO Virgo detectors will start again soon, and they will have increased accuracy, increased sensitivity. So in the future, it's clear you need better and better description of the motion of two black holes and the waveform they emit. Over the last years, quantum and also classical scattering approaches have given a new viewpoint. They are bringing conceptually interesting new results, not yet of direct interest for LIGO. Okay, in all the papers they say it's crucial for LIGO. It's not true. Maybe in the future they will really bring something new. For the moment, this is conceptually very interesting, and we try to extract information. I doubt that, because they are reaching the limits now of the number of loops they can compute. Why? With the tutti frutti methods, we went up to 6 loops, you know. So it will be very, I don't think they will ever be able to compute the things we were able to compute in the slow velocity regime, but we will see. I'm open-minded. And to conclude, I will end with this formula, this sentence of Henri Poincaré, who worked, you know, on the celestial mechanics for all his life. And at the end, he said, there are no definitely solved problems. There are only problems which are more or less solved. As you say, the real hard problems of physics, you know. For instance, myself, I thought I had solved the two-boundary problem when years ago I computed this PPM. Okay. Now I realize you need to go on, but you learn new things, and there are new technologies, and everything is for the future. And there are many things for the young people to do in this thing, because gravitational wave is just starting, you know. It's going to be here for hundreds of years. Okay, thank you for your attention.
Questions or comments from the audience?
Most of you, what you said is for non-rotating black holes.
Yes.
Yeah.
Yes.
So
the effective one body has been has been developed for spinning black holes. It's not. I mean, many technical thing changes. You need to add spin-dependent terms. All the information we had in post-Newtonian and post-Minkowskian are used for this, but the EOB dictionary exists. So that is to say, given any results on spinning things, you can include them in a spinning Hamiltonian. And this is quite important for the Hamiltonian and for the waveform. So all this, I should have mentioned.
Other questions? Okay.
In the scattering approach to the problem, there is a sort of separation of time scales, which is behind. I mean, scattering takes an infinite amount of time to take place. Mm-hmm. On the other hand, you want to use the two-body scattering to describe what happens in the final stage, the interaction of the black hole. So yes. How should I interpret this scattering theory?
So for the moment, the scattering information is used to, although Rafael Porto has said you can sometimes use shortcuts, but essentially, conceptually, like I've shown here, you can transform the scattering angle into an Hamiltonian. And although this Hamiltonian describes the scattering, the same Hamiltonian, which is 1/r plus 1/r squared, can be used to describe the last orbit. Okay. What is lacking here is you need radiation reaction, and you need radiation reaction in the last orbits too. While scattering gives you radiation reaction when they are far apart. So the question is, can you transform this information also for the last? And as soon as you can describe things by mathematical objects which are function of parameters, if you have, for instance, a Newtonian function of distances and velocity, you can apply, this is my way of seeing things, okay? It's just a tool to get the higher order things. But you don't need the scattering to describe directly the coalescence. Actually, it's not at all. Except that in some cases, by analytic continuation, but this is for bound states or for additive effects, I think we need to go for intermediate steps.
Okay.
Very naive question. Something I missed is the quantum part of the talk is just something that is used in analogy with the computation, or you really have some quantum mechanics in your...
No, it's really a quantum mechanics, and you use Feynman, except that you cannot use, it would be a Feynman amplitude computation, really quantum, except that there are much better methods. If you were writing Feynman rules, you would have millions of terms, or 10 to the 80 terms in some cases, while you have shortcuts to compute. But it's a quantum computation, but you need to, the quantum computation contains many other effects, really quantum effects and classical interaction effects. So you need to disentangle in your computation, and you try to do it at an early stage, because if you do the full quantum computation, it's extremely difficult, nobody can do it. And then at the end, you would have to throw away many terms. So they try to do it early on, saying, okay, in this diagram, I keep only this and this, and I have this technique, which immediately gives me the classical part. But it is like a black art in the sense that...
Yeah, but at the end, you keep only
you keep only the classical part.
And at the beginning, you only...
Let's say the naive way, which is not naive, is in the econal approach, this is saying, in the WKB limit, the transition amplitude is exponential of the classical phase, IS over h bar. So you want what is in the exponent with IS over h bar. Okay. So you extract it from a quantum. But what is remarkable is quantum techniques, really, using analyticity properties in some variables, is very efficient to compute what you want. Remarkably efficient.
Because you're operator.
Because, sorry?
Because behind the operator.
Yes, so the Dyson expansion and all that and gives you, indeed, to me, it's still partly mysterious why the classical thing where that's what you want. Maybe there is a better way to organize the classical so that it is as good as the quantum. This is an open problem.
Yeah, so you mentioned that as one of the puzzles that at order d3, you had an energy loss which was even bigger than initial energy. So do you think this is an artifact of your approximations, or is rather to do with a wrong notion of energy to start with?
No, it's not the wrong notion of energy. It is, first, it can be a non-commutativity of limits because it is the high energy limit of the G-cube thing, which is bad, okay?
Right, exactly.
Okay, so there is this non-commutativity.
Yeah.
But then, okay, what still probably happens is that you have an expansion and higher order terms in the ultra energy limit becomes as important as the lower order term and modify it, something like. So we still don't know very precisely this perturbative expansion, what are its properties, okay? And how to use it at ultra energy. Gabriele Veneziano has proposals along this.
May I ask you another question? Concerning the very last part, there is this emission of gravitons. How do the soft theorems help in deriving this result?
They help mainly to checks. Like you can check that in the limit, in the soft limit, all those terms combine to, and you can recover the Weinberg simple formula back. But then, for instance, in this
Just a
ah,
moment.
just a moment.
Okay.
Yes. Here, you have many terms. In the soft limits, you need terms from all over here to recover the Weinberg soft theorem. So it is a check that you computed them correctly, So soft limit is very useful because Weinberg long ago found that there are very simple approximations when you emit very soft, very long wavelength gravitons from any process, even a hard process. And so it's used as a tool.
But recently, Kashas and Soninger extended Weinberg soft limit to the subleading term, which is so this could help further in constraining the results.
In constraining, yes, in checking things, not in getting this result, as far as I know. Okay, they tried, like Rodolfo Russo also was trying to say these puzzles at ultra energy. They said, in the soft limit, it changes character and there is a cutoff, but it's not a proof that this cutoff applies outside of the soft. So it is a tool. It's not solving problems immediately for yourself. I mean, you cannot have both le beurre et l'argent du beurre, as we say in French.
I have a very general question. When you say you write in Hamiltonian, you treat this black hole as a particle?
Yes, thank you for this question. I should have said this is linked to the method of matched asymptotic expansion that actually I had proven long ago in the 80s that although black holes are expanded objects with a structure, and they even have a non-zero love numbers if you ask for the first love numbers, which is that black holes are deformed by each other tidal forces, but that does not introduce and induce quadrupole moment. I have shown that the second love number of the black hole is 0, which means that up to 5 loop, actually, you can replace 2 black holes by point masses if you regularize. But when you put point masses in general relativity, now you put distribution sources in a nonlinear set of PDs. And it's not well defined. But if you use good regularization methods, and as far as we know, and one can prove this up to some order, but not to all orders, dimensional regularization, which is to work in a space-time with 4 minus epsilon dimensions.
Okay.
With epsilon complex parameter that goes to 0 at the end of the calculation, all the results are finite up to 5 loop, okay? And do not depend on having replaced the black hole by point masses. Beyond this, it is not known if it is true. So one needs to, but in principle, match asymptotic expansion, which is not really proven mathematically, but is a very efficient method, can prove this.
And all the series you've shown us are asymptotic series.
Yes, yes. But still you can reason.
No, okay, okay, work. Okay, so maybe we can stop here. So thank you very much again for your talk. Let us close this.